Excuse me. Advent of Code 2024, Day 17. Chronospatial Computer. The historians push the button on their strange device, but this time you all just feel like you're falling. That's 2018, Day 6. Situation critical, the device announces in a familiar voice. Bootstrapping process failed, initializing debugger. The small handheld device suddenly unfolds into an entire computer. The historians look around nervously before one of them tosses it to you. Why not? This seems to be a 3-bit computer. This program is a list of 3-bit numbers, 0 through 7. Oh, good. Are we doing a VM? We didn't do any VMs last year. I was kind of disappointed, but it looks like this year's going to be a VM. Yeah, I'm just scanning ahead. We got operands and instructions. And its program is a list of 3-bit numbers, 0 through 7, like 0, 1, 2, 3. Okay. The computer also has 3 registers named A, B, and C, but these registers aren't limited to 3 bits and can instead hold any integer. All right. Maybe we'll go with like I64 for now. The computer knows 8 instructions, each identified by a 3-bit number called the instruction's opcode. Each instruction also reads the 3-bit number after it as an input. This is called its operand. A number called the instruction pointer identifies the position in the program from which the next opcode will be read. It starts at 0, pointing at the first 3-bit number in the program. Except for jump instructions, the instruction pointer increases by 2 after each instruction is processed to move past the instruction's opcode and its operand. Right? That makes sense? The computer tries to read an opcode past the end of the program. Excuse me. Past the end of the program, instead halts. So the program 0123 would run the instruction whose opcode is 0, pass operand 1, instruction out opcode 2, pass operand 3, and then halt. That makes sense. There are 2 types of operands. Each instruction specifies the type of its operand. Okay. The value of a literal operand is the operand itself. For example, the value of the literal operand 7 is the number 7. Value of a combo operand can be found as follows. Okay, so it's a way to read registers. 0 through 3 are 0 through 3, 4, 5, and 6 are A, B, and C, and a combo operand 7 is reserved. Oh, maybe that'll be part of part 2. 8 instructions are as follows. ADV performs division. All right, the numerator is in the A register. The denominator is found by raising 2 to the power of the instruction's combo operand. So an operand of 2 would divide A by 4, 2 squared, right? Okay, an operand of 5 would divide A by 2 to the B, because combo operand 5 is B. I think I understand. The result of the division operand is truncated to an integer and then written to an A register. Okay. BXL calculates a bitwise exclusive OR of register B with a literal and restores result in B. BST calculates the value of its combo operand mod 8 and writes that value to the B. Okay. JNZ does nothing if the A register is 0. However, if the A register is not 0, it jumps by setting the instruction pointer to its literal operand. Okay. If the instruction jumps, the instruction pointer is not increased by 2. Got it. That makes sense. You're jumping to a location. BXC calculates a bitwise exclusive OR of register B. So that's the same as XL. Oh, but it's register B and C. Got it. Whereas this is B and a literal operand. Understood. For legacy reasons, this instruction reads an operand but ignores it. Because it's using C. Got it. Out. Out calculates the value of its combo operand, mod 8, and then outputs that value. The program outputs multiple values that are separated by commas. All right. BDV works like ADV, except the instruction is stored in the B register. Oh, the result is stored in the B register. The numerator is still read from the A register. All right. And then CDV has the same semantics. We store it in C, but we still calculate it the same way. Okay. And then we have some examples. Here's a little program that outputs this. Here's another example. The historian's strange device is finished initializing its debugger and displaying some information about the program it's trying to run, which is your puzzle input. Okay, let's see how big this program is. Get input 2024 J17. Oh, that's tiny. Usually these programs are very long, but this is all we get. All right. For example, here's an example program. Your first task is to determine what the program is trying to output. To do this, initialize the registers to the given values. Right? That's the same here. We have some values. Run the given program, collecting any output produced by the out instructions. Always join the values with commas. After the above program halts, its final output will be this, using the information provided by the debugger initialized. So what do you get if you use commas to join the values it output into a single string? Okay. We can do this. Let's make a machine. State computer, no, struct computer. We have an A register. They said it can hold any value. And then we have a program, which is just going to be a vec of, we don't have anything that goes as small as 3 bits, so let's use 8 bits. And then we have an instruction pointer, which is going to be indexed into the program, so we'll make it a usize. So let lines equals ASCII read lines, this. And then let's just put the computer here. And we can say self device equals computer from lines, let's say. And we just need to implement that extract into variable. No. Oh, we need to make sure it's default, right? And let's create from. Oh, we can't. Why not? Oh, because I'm using from, and from is a trait. From lines. There. Generate from lines function. That's what I'm looking for. Okay. So lines of 0 is going to be the A register, right? We can actually write a little test build computer. Let computer equals computer from lines. And instead of a vex string, we're going to do, I think this is the more normal way to do it, right? And then we can just put these lines in here. Copy. Paste. Like this. Oh, this should be a slice. Yeah. Okay. And now we need to assert EQ that 729 is computer A. B and C are both 0. And the program, oops, I forgot the bang. The program is going to be this. And then finally, we want to assert that the instruction pointer is 0. And right now we don't have that. Oh, I'm surprised this didn't do self here. Okay, so let's hit test. Oh, it doesn't even build. Oh, because I need to put an ampersand here. Okay. If I say self default, then the test should run and fail. 729.0, yes. Okay. So the first line is register A, then register B, then register C. And now our input is exactly the same. So I'm going to assume the format is that, and I don't need to even pay attention to anything before this. So I can say let A is equal to lines of 0, split once on, on colon space. We'll take the first parameter, unwrap it first, and then do the first argument, and then we're going to say parse I64. Well, we shouldn't have to say that. Unwrap. Because we're going to put it right in the thing. Here's B, here's C on lines 1 and 2, and then on line 3 is the program. So this is going to be lines 3, split once, colon space, unwrap 1. And now we're going to split on comma. We're going to map that. No, let's just say num. Say num parse unwrap collect, and now say self abc prog ip colon 0. And that passes. Okay, so that test passes. And now we need to actually write the code to do a step. So let's do a single step. And then we'll write a little thing that runs and generates output. That seems like the right approach. So ADV instruction performs division. So we're going to say fn step is going to mutate ourselves. And then, so we get the instruction, inst equals self prog self IP. We get the operand. Plus 1. I was already thinking that we want to increment past the instruction, right? So this performs division. So let's say we can match on the inst. And if it's 0, the numerator is the value in the A register. The denominator is found by raising 2 to the power of the instruction's combo operand. Oh, okay. Let's do this. Let's call this the literal. And let's call this the combo. Match literal. 0 to 3 becomes literal. 4 is self A. 5 is self B. 6 is self C. And 7 is panic invalid operand combo operand literal. Okay, so now we have the literal value and the combo value. So we're going to divide A, and we're going to store the result into the A register. It's truncated to an integer and it's written to the A register. Okay, so self A equals, self A is the numerator, and then it's 1 to the combo. Yeah. Okay, that's right. BXL, bitwise exclusive OR of register B and the literal operand. Okay. Self B is self B. Oh, I know that the caret is exclusive OR in C. Is it also in Rust? Yeah. Bitwise exclusive OR operator. Okay. Don't need that maze anymore. Exclusive ORed with the literal. Okay. Instruction 2, the value of its combo operand mod 8, and puts that in B. Self B equals self B mod 8. Okay, J and Z. It does nothing if the A register is 0. However, if the A register is not 0, it jumps. Okay, so if self A equals, oh, yeah, we can say if self A is not equal to 0, then we can say self IP equals jumps to literal operand. Okay. Opcode 4, bitwise exclusive OR of B and C, and it stores it in B. Okay, out instruction. How about this? How about step returns an option I64. And what we'll do is we'll set it to none here, and here we'll just say output is equal to some calculates the value of its combo operand mod 8 and outputs that value. Okay, so combo mod 8. All right, instruction 6. BDV. Oh, right. It was the same as ADV, except we store it in the B register. So self B is self A 1 combo. And 7 is self C, self A divided by 1 combo. And then everything else is panic. Oh, no. 3 without this is do nothing. And everything else is a panic. How's that? And then we output the output. Yeah, that should work. Oh, literal is a U8. Okay, so we can do this as I64. Oh, and this needs to be as usize. Got it. Oh, right. There. All right, and we're not using step, but we can do step, right? We can run this little example program. I guess we can't just do a step. We could do one of these. Let's just try running this and see what happens. Let's write a program called run, or a function called run. Which just runs step until IP while self IP is less than self prog len. Self step. And then this will return a vec of I64. If let sum output equals self step, then we're going to push it on to the result. And that'll be the program. Let's test this. And this should output this vector. Okay. Let result equals computer run. Oh, I need to make it mutable. And then we're going to say assert EQ, vec bang, this result. Okay. Oh, and it worked. It probably should be 2 separate steps, right? Let's do that. Test output And then this doesn't need to be mutable anymore. Okay. So I think we got this right. I mean, this was hard to get wrong, right? So now we just need to, what do you get if you use, oh, yeah. Okay, so part 1 is going to be device let output equals device run. I think this isn't going to work, right? Self-device run, right? Yeah, I don't have anything that can display it. So we can do output. Oh, I can do, oh no, but it's going to put spaces, right? If I say format bang output like that. Ooh, invalid combo operand 7. Oh, right. Because if it's a literal, it's a literal. We should just ignore it, right? So I should just say this. And just live with it. It should all just work. Yeah, so now I probably need to combine it with, yeah, without the spaces. Okay. Let's say output is this iter map num to string collect vec. That's a little awkward, but I think it'll work because then we can say here output join comma. Yeah, so this is my answer. Let's see if this is right. Oh, that's not the right answer. Huh. I mean, the test code works. And I'm reading the correct file. Maybe there's one of these instructions that's not in here. Yeah, so this is testing 0, 5, and 3. And that's all it's testing. Whereas our program is a little more complicated. We have 2, 1, 7, 1, 0. Okay, so there might be something I misunderstood here about the instructions. So let's take a look at these instructions again. The numerator is the value in the A register. The denominator is found by raising 2 to the power of the instruction's combo operand. Right. It's truncated to an integer. Yeah, we do that already because these are all ints. So BXL calculates bitwise exclusive or register B and then literal. BST. Oh, this is what I got wrong. It's a combo mod 8. Okay, what else did I get wrong? This is jump, right? And it's doing to the literal. This is B and C, so it's neither literal nor combo. Output C combo, mod 8. And then these both use combo because they use the same thing as 0 up above. Save it here. Save it here, spotted it already. Thanks. All right. So now I have a different answer. Let's try it. Hey, that's the right answer. Okay, so that was the bug. I just messed up that. All right. Git status, git add source, git commit -m 2024 day 17 part 1. That is done. All right, let's see what part 2 is. Digging deeper into the device's manual, you discover the problem. This program is supposed to output another copy of the program. Oh, Quine, right? That's what they're called, I think. Unfortunately, the value in register A seems to have been corrupted. You'll need to find a new value to which you can initialize register A, so the program's output instructions produce an exact copy of the program itself. Oof. This program outputs a copy of itself if register A is instead initialized to this value. The original initial value of register A is 2024 is ignored. What is the lowest positive initial value for register A that causes the program to output a copy of itself? All right, well, it's time to disassemble the program, I think. This is the program. So let's just create a scratch file here and decode the program. Let's get our instructions again. All right, so we have 2.4. 2.4 is BST, the combo. Let's do this again. BST, the combo. 4 is A. Okay. No, yeah, BST A, which means B is equal to B exclusive ORed with A. Okay. We have 1.7. 1 is BXL, which is B and the literal. So 7. B is equal to B exclusive ORed with 7. Okay, so just flip the bits. Then we have 7.5. 7 is CDV. With 5. 5 is the B register. Oh, no. B. Yeah, 5 is the B register. Okay, so. Yep. So this is going to be equal to, C is equal to A, the value in the A register divided by 1 shifted by B. Yeah, got it. I confused 2.4 with opcode 1. Oops. Oh, yeah, BST calculates the value of the combo operand mod 8. Ah, thank you. Wait, yeah, 2A. Oh. Got it. So this is A mod 8. Understood. Okay, and then we have 1775, 17 again, which is BXL7 again. Okay, so we flip the bits back after doing something with C. Then we have 0.3. 0 is ADV with the value 3, which means A is equal to A divided by 1 to the 3. Okay. 4.1 BXC, which is a bitwise OR of register B and register C. The 1 doesn't matter, so B is equal to B exclusive ORed with C. Then we have 5.5. Output the B register. And then we have 3.0. And 3 is the jump instruction. Just go to 0. All right. This means C is equal to A shifted by B, right? That's what that means. And then this means A is A divided by, or shifted by 3. So what is this doing? It grabs a value from the A register, mods 8. So it takes the smallest 3 bits. It flips them. It then shifts A down by whatever value this is. So this could be 0 to 7. It then flips the bits again. I'll output B mod 8, thank you. It flips the bits again. And then it shifts A down. It does an exclusive OR with C. And it outputs the result and then loops back to the beginning if A is not 0. Right, I should put that there. If A is not 0, go to 0. And then halt. Okay. So right now what it's outputting is, okay, so wait a minute. It's taking that number from the A register. I think I see what's going on. It's taking like the lower 3 bits from the A register. It's doing some manipulation to it. Right? B is flip the bits. Flip the bits again. So these actually kind of cancel out. Oh no, they don't cancel out because that determines how many bits to shift here. If it puts them back the way they were, then it shifts A down by some amount, by 3 bits. It does one more bit manipulation and outputs that value. And then if A is not equal to 0, in other words, we haven't shifted all the way down to nothing, then do the whole thing all over again. All right, I'm going to save this file. Let's play around with this a little bit. Let's see what happens for various values of A. For A in 1 ... I don't know. We're doing 3 bits. So we care about those. Oh, it's not just 3 bits, right? We're doing 3 bits plus however many bits are in here, which could be 0 to 7. More bits. So we can play with 10 bits. Which is 1024, I think. Yeah, 1024 is 10 bits, 2 to the 10th. Let's just dump out all those and see what those look like. Oh, I messed around with the device in part 1. Let mut device equals self device. We'll have to add clone to it. Right, that way we don't mess around with it. Oh, we could just do a reset. Let's just do a reset rather than having to mess around with cloning and things like that. Because the program isn't changing. The only thing that's changing is the registers. So if we write a reset, B, C, and IP. That's all we care about. So we can say self device reset, self device A is equal to A. And then we can do this. Why don't we do this inside our run? Because this is what we need, right? Is the comma separated. Oh no, we want to check to see if the program, okay, yeah. So we want to see what it looks like. So we'll just say let println A:4 and then the output self device run. And this is going to generate 1,000 lines, but that's okay. We're just trying to take a look. Okay. All right, so we can see that everything's getting messed around with. I mean, there's no like set order, so we can't do like a binary chop and find it that way. What do we start with? 24177. Okay. So we know that we need to manipulate the first 10 bits. Let's reason this through here. We know we need to manipulate the lower 10 bits in order to manipulate the first value. But after that, any additional changes won't affect the lower 10, the first digit. Right? Because we do up to 7 here and 3 more. Huh. So if we find, so in this list, there's a bunch of, oops, I had B and it reran it. That's okay. There's a bunch of entries that start with the number 2, right? Because that's our first digit is 2. Here's one, for example. And the next one is 4. Well, we know that if we add more bits to it, it's not going to change these values, or the first value. Because we only care about the first 10 bits. And then we shift 3, and then the next 10 bits matter to generate that next number, the 4. And after that, the 1, and then all the way down to 0. Okay. I might have a plan. Let's save all the entries that start with a 2 after we run them. If output of 0 is a 2, actually we should check self device prog 0, right? We want to make it generic. So we can save this A, saved push A. And after we're done with that, we should have a list of numbers. What is this? The vec of I64. Oh, and as prog is U8s. Sure. All right, so these are all our candidate numbers, right? Every one of these generates a 2 in the first position. What we can do is, let's see if we can generate the second number, and we only care about 3 bits at a time. So we can say for bit in 0.8, we have a saved value for consider in saved. What we do is we take the value we're considering, self device reset, self device A is equal to the value we're considering and the bit. So it's going to be bit shifted by 10 or consider. And then this should give us our second one, right? We'll now get the output here. We're going to assert that we haven't changed the first bit. Output 0 is equal to self device prog 0 as I64. All right, so now we're going to look at the output 1. Then we should have a number, another number to consider, right? Oh, I need to save it, right? Let's see. Let num equals println num output. So this should generate all the 2 followed by 4. If I don't mess up my code. Ooh. Oh, right, right, right. We have to make sure that we have at least that many, if output len, because small numbers only have one value. It's greater than 1. And there. Yeah, so now everything starts with 2, 4. And I can see some 2, 4, 1s already. Yeah, 2, 4, 1, 7, 7. Okay, I think we're on the right track. How do we expand this to be generic? Let's do it this way. We can say our position is 1. We're now considering, yeah, we don't have to worry about this. We're going to assume we have the code right. So this changes to position. And this changes to position. This changes here. We're going to want to shift up 3 bits per position. So this would have to be 7 plus 3 times the position. And then we want to also say while position is less than self device prog len. I don't want to dump out a million outputs though, right? We want to actually modify the saved. Let next is equal to vec new, because we need to, every candidate number we find, we need to use next time. So next push num, and then at the end of the loop here, we'll say saved equals num. Println, oh, next. Pause, they say pause like this. Next. Does this look right? No, it doesn't. First of all, I do need to increment the position each time. This is what, see, Rust is really helpful. It tells me I haven't written all my code. I intended to mutate it and I never did. So, all right. Is it infinite looping or did it finish? Oh no, it finished. What am I looking at? I'm looking at a bunch of numbers. Oh, okay, yeah. So each position should have those number of positions filled in then. What's the answer? The lowest positive initial value for register A that causes the program to output a copy of itself. Okay. So let's see. Let's not print this out. We should have now inside saved all these guys here. We just need the minimum. And oh, that's a reference to an i64. Is that what these are? No. Okay, well, whatever. I should be able to now say self device reset, self device A is equal to min, self device, and then say this, println. We're going to print out the output of the program, self device prog, and we're going to check it against what we got. Output is run. You have to spell println correctly. Yeah, look at that. Oh, now we need the number. All right, there we go. Hey, that's the right answer. Okay, that was fun. That was fun. I know there are people who don't like doing this kind of code analysis to figure out what's going on and stuff like that, and people will bail. when I see problems like this. I don't mind them. They're not my favorite, but I don't mind them. They're always tractable.